Hello everyone, I'm here to explain about the ANN models, GPU, and cloud services. Now, let's start with understanding what artificial neural networks or ANNs really are. They are inspired by the human brain, which uses networks of neurons that process information in ANNs. We have artificial neurons that work similarly, passing information and learning from the data. ANNs are built using layers, which are the input layer that the data enters, the hidden layer in the middle where the real processing happens, and the output layer that provides the result. During training, the network adjusts the connections or the weights between these neurons to reduce errors, enabling it to learn patterns. Now, what are ANNs used? They are applied in the areas like image recognition. Uh, like for example, think of how a phone can be unlocked by recognizing a face. They are also used in natural language processing, like in chatbots that understand our questions. So what's special about these ANN is they capture the hidden and the complex patterns, especially in the areas that traditional algorithms might fail. That will to see the deep connections. Let's move to the next slide. Structure of ANN. Now let's break down the components that make up the ANN. Starting with the neurons, each neuron is a tiny processor. It takes inputs, applies a weight to each input, sums them up, and applies an activation function to produce an output. Imagine like this, some processing, multiple clues to come up with a final answer. Then we have the layers. The first is the input layer, which receives the raw data, say an image or a text file. Then we have the image. Then we have the hidden layers. These layers do the heavy lifting refinement happens in the data. Finally, the output layer, which provides the end result by predicting the label or a value. Now, about the weights. Think of the weights as the strength of each connection. During training, weights are adjusted to improve predictions, making the model smarter over time. Lastly, the activation function. They add non-linearity to our network. Functions like relu, which outputs zero for negative inputs, help the network learn complex patterns by introducing flexibility. Sigmoid or tan are also common, especially when we need outputs between specific ranges. Um, Let's so here we can see the structure of ANN, where this is the input layer where the data enters, and hidden layer where the processing happens, and this is the output layer where where we get the output from. Now let's see how ANNs learn. This process depends on three main things: weights, activation function, and back propagation. As we discussed earlier, weights control the strength of connections during the training. The network can constantly adjust these weights based on errors. For example, if prediction is wrong, the network tweaks the weights and tries to adjust to get it right the next time. Then we have the activation functions like relu, sigmoid, and h. These functions introduce nonlinearity properties to the network, allowing it to learn more complex relationships. And finally, we have backpropagation. This is the method where the network takes the error from its predictions and sends it backward through these layers. By doing this, it knows which weight to adjust while improving accuracy. So, backpropagation helps fine-tune the network, making it better with each pass of data. Let's move to the next slide. Applications of AI. Now that we know how agents work, let's look at some real-world applications. The first is the image recognition, where agents are excellent at identifying objects or faces in image. This technology is used everywhere from facial recognition on the phones to medical imaging, where it helps in diagnosing diseases. Then we have the natural language processing (NLP), where agents help machine learning uh, where ANNs help machines understand human language. Chatbots, for example, use ANNs to then there is natural language processing or NLP, where ANNs help machine learning machines understand human language. Chatbots, for examples, use ANNs to interrupt operations and respond accurately. Another area is predictive analysis. In fields like financing and marketing, ANNs look at the past data to forecast future trends, helping companies make better decisions. Some real-life examples include self-driving cars that use ANN to detect objects around them, or banks using ANN for fraud detection, and e-commerce sites offering personalized recommendations. These applications show how versatile ANNs are. Now, let's see the types of algorithms. ANNs have different types of architectures, each designed for specific type of data and tasks. The most basic type of feed-forward neural network, FNN, where the data flows in one direction from input to the output, making it good for simple classification tasks. Next, we have the convolutional neural networks, or CNN, which are built to process images. They work by focusing on small regions of input of image at a time, making them highly efficient tasks for facial recognition or object detection. Next, we have the recurrent neural networks, or RNNs. They are designed for sequential data like text or time series data. They can retain information from the previous inputs, making them ideal for tasks like language translation or stock price prediction. Deep Next, we have the deep neural networks, or DNNs. They have multiple hidden layers, enabling them to capture more detailed and complex features. They are used in tasks that require intricate pattern recognition, like, for example, we can say speech recognition. And lastly, we have generative adversarial networks, or GANs. They are made up of two competing networks. One generates data, whereas the other evaluates it. This unique setup is, uh, is used for creating realistic images, videos, and even virtual environments. So, these type of ANNs have specific role depending on the problem we are trying to solve.
Feed-forward neural network. The feed-forward neural network is the most straightforward type of neural network where data flows unidirectionally from the input layer through the hidden layers to the output layer. FNNs are ideal for simpler tasks like binary classification, linear regression, and pattern recognition in datasets with straightforward relationships. Because of its simplicity, FNNs are computationally effective and easy to train compared to more complex networks, making them a good starting point for beginners and educational purposes. Their streamlined structure makes them particularly suitable for small datasets or basic tasks where relationships are not highly complex. Convolutional neural networks are designed specifically for image data, as they can detect spatial patterns through layers of convolutional operations. Convolutional layers apply filters to detect features like edges, textures, and shapes, while pooling layers downsample the data to reduce dimensionality. This structure allows CNN to focus on local patterns, making them highly effective in image-related applications. CNNs are widely used in facial recognition, autonomous driving for object detections, medical imaging for disease identification, and augmented reality. Their architecture enables them to process large volumes of data, efficiently identifying patterns that are crucial for decision making in fields requiring high accuracy. Recurrent neural network. RNNs are designed to handle sequential data by incorporating feedback loops that allow information from previous input to influence current outputs. This makes them ideal for applications like language modeling, where context from early words can affect predictions for subsequent words, as well as for tasks involving time series data like stock prices or weather forecast. RNN maintains a memory of previous inputs, making them suitable for tasks that depend on understanding sequences and contextual information such as speech recognition and image transmission. Deep neural network. DNNs are neural networks with multiple hidden layers, allowing them to model complex relationships by extracting high-level features from data. This deep structure enables humans to process vast amounts of data and learn intricate patterns, making them effective in applications that require advanced data interpretation, such as natural language processing and high-dimensional data analysis. Renans are versatile and powerful, often used in applications like image classification, voice recognition, and sophisticated predictive modeling, where detailed feature extraction is essential. Generative Adversarial Network (GANs) consist of two neural networks: a generator that creates synthetic data samples and a discriminator that evaluates their authenticity. GANs are known for their capability to generate new, realistic data by learning from existing data. They are used in image synthesis, deepfake technology, data augmentation, and creative fields like art and music generation. By having two networks compete against each other, GANs can produce high-quality synthetic data that closely resembles real data. Challenges in training ANN. Training ANNs presents several challenges, like computational demand. ANNs, especially deep neural networks, require extensive computational power, making training time consuming. GPUs are recommended for handling the parallel processing demands. Data requirements. ANNs require large labeled datasets to perform well. Data preparation and cleaning are essential to ensure model accuracy. Overfitting. ANNs may perform well on training data, but poorly on new data. Regularization techniques like dropout and L2 regularization can help mitigate overfitting. Interpretability. ANNs are often considered black boxes, making it difficult to understand decision-making processes. Methods like LIME and SHARP can help enhance interpretability, providing insight into the model's prediction. Accelerating ANN and training GPUs. GPUs accelerate ANN training through parallel processing, which is essential for handling the complex metric operations required in deep learning. Unlike traditional CPUs, GPUs have hundreds of cores, enabling faster computation. Frameworks like TensorFlow and PyTorch support GPU acceleration, boosting performance. Using GPUs allow researchers to train larger models more quickly, leading to faster experimentation and deployment of advanced models. Summary and classification. The final slide recaps the versatility of ANNs in various applications, from image recognition to NLP. Different architectures like CNNs, RNNs, DNNs, GANs serve specific data types and problem requirements. Key challenges in ANN training include high computational needs, data quality issues, risk of overfitting, and the need for interpretability. Solutions like GPUs and cloud services like Google Colab, Kaggle, AWS make it possible to scale ANN training, making these models accessible and adaptable for a wide range of products. So I think you understood about the topics we discussed. Thank you.